Hello and welcome to the Unit 9 Section 1 video on two-dimensional figures. So we're going to start off by talking about the area of several different types of figures, and the first figure we're going to talk about is the area of a parallelogram. That's going to be our starting point. Very much like parallelograms were our starting points for quadrilaterals in Unit 7, that's going to be our starting point here in this section of Unit 9. Now, a tangram is an ancient Chinese puzzle made from a square. Okay, an example of the pieces of a tangram are given to you there on the right. The pieces can be rearranged to form many different shapes. In this case, we have a shape of a swan. The area of a figure made with all the pieces is the sum of the areas of the pieces. And that gives us the area addition postulate. So you notice we've got a lot of addition postulates here in geometry. We started with segment addition and angle addition in Unit 1. In Unit 8, we added on the segment addition postulate for circles, and now we have the area addition postulate. Recall that a rectangle with base b and height h has an area of the base times the height, or you may more commonly refer to it as length times width. You can use the area addition postulate to see that a parallelogram has the same area as a rectangle with the same base and height. So here we have a parallelogram. If we take this triangle portion of the parallelogram and move it over to this part of the figure, we end up with a rectangle, base times height. So we can use the same formula to find the area of a parallelogram, and that is indeed the area of a parallelogram. It is the base times the height. If you know what the base of the parallelogram is and the height is, you can find the area. Remember that rectangles and squares are also parallelograms. So the area of a square with the side s is s squared, and the perimeter is 4 times s. Remember that a square is a parallelogram, so is a rectangle. So it makes sense that you can use the same formula to find the area for all three. So let's find the area of the parallelogram given here. Well, we need to know what the height is. We're given what this length is, we're given what this length is, and if we extend the base out to get what the height is, we have a right triangle. Okay, so we're going to use the Pythagorean theorem, which is our 3 squared plus our height squared is going to be equal to our hypotenuse squared, which is 5 squared. So 3 squared is 9. 9 plus h squared equals 25. So h squared is equal to 16. So h is going to be 4. And it has to be positive 4 because we know that length has to be positive. And so now we're going to use this in our area equals base times height. The base is 6. The height is 4. And so the area of our parallelogram is 24, and you have to put the units on it when you're given units. So in this case, it's going to be square inches. The area of triangles and trapezoids behave very similarly to each other, so we're going to talk about both at the same time. Notice that two congruent triangles or two congruent trapezoids can fit together to form a parallelogram. So here we take this triangle and we create a copy and place it upside down and make a parallelogram this way. Same thing with the trapezoid. We copy it, turn it upside down, fit it together to make a parallelogram. Well, we know that the area of a parallelogram is the base times the height. But since we only need half of this parallelogram, we're going to take half of it. And so that gives us the formula for both a triangle and a trapezoid of being 1/2 base times height. Now, for a trapezoid, you're going to add the bases together and then take half of it and multiply it by the height. So, example 2 here, we want to find the area of a trapezoid with these two bases and this height. So, area equals 1/2 base 1 plus base 2 times the height. So we have 1/2. Base 1 is 9, base 2 is 12, our height is 3, and when you do all that math together, you're going to get 31.5 and our units are going to be centimeters squared. Now for the area of a rhombus and a kite, these are going to behave similarly. A kite or a rhombus with diagonals D1 and D2 can be divided into two congruent triangles. Okay? So let's find out what the area of these triangles are. Well, the area of a triangle here is going to be 1/2 of the base times the height. Okay, so our height is 1/2 D2 and our base is D1. So we multiply D1 by 1/2 of D2, which is this part, and we take half of it, half of the base times the height. Here's 1/2, here's our base, here's our height. 1/2 times 1/2 gives us 1/4, D1, D2. So this is the area of this triangle, but we have two of these triangles. So we have to multiply it by 2 to get the area for the whole thing. 2 times 1/4 gives us 1/2, so our formula is going to be 1/2 diagonal 1 times diagonal 2. That works for the kite as well, and so we have one formula for two different shapes. So let's do example 3. We are told what one of the diagonals is, we're told what the area is, we want to find what the other diagonal is. So we're going to use our formula, area equals 1/2 D1 times D2. Our area is 48, D1 is 16, and we're trying to find D2. Well, half of 16 is 8, and we do 48 divided by 8 when we divide each side by 8, and we end up with D2 being 6 centimeters. Not centimeters squared, because here we're just talking about the length of the diagonal. So now let's move on and talk about the circumference and area of a circle. Recall that a circle is a set of all points in a plane that are equidistant from the center of a circle. The irrational number pi is defined as the ratio of the circumference, c, to the diameter, d. This is where pi comes from. It's the circumference divided by the diameter. And if you take the circumference and divide it by the diameter of any circle, that will give you 3.14, 15, so on. Solving for c gives the formula c equals pi times d, but we know that d is also 2r, so our circumference is 2 pi r. You remember from the last unit we used that for circumference when we did the arc length. So you can use the circumference of a circle to find its area. Divide the circle and rearrange the pieces to make a shape that resembles a parallelogram. Again, we're going back to parallelograms here. So if we divide this circle into 8 pieces and rearrange them, you have a parallelogram here, but you also have a little bit extra that's not accounted for. But you approximately have base times height, which is pi r squared. That gives us area. The more pieces you divide the circle into, the more accurate the estimate will be, because we end up with less and less overlap the more pieces we have. So the circumference of a circle is 2 pi r, and the area is pi r squared. So let's use those two formulas to do a few examples. So in example 4 here, let's find the area of circle P in terms of pi. Well, area is pi r squared. So we're going to have pi times r. Well, r is not 16, that's the diameter, so you have to take half of 16 to get the radius, which is 8. And so 8 squared is going to give us 64. So we have 64 pi centimeters squared. It did ask for our answer in terms of pi, so we're done. All right, let's find the radius of circle X, where the circumference is 24 pi. Well, we know that the circumference is 2 pi r. If the circumference is 24 pi, and we know 2 pi r is on the other side, we can find the radius by dividing each side by 2 pi, and so we get our radius is 12 inches. Example 6, find the circumference of circle S in which the area is 9 pi centimeters squared. So we know that the area is pi r squared. The area here is 9 pi, and so we're going to find what r is. 9 is r squared, so r is 3. Our radius is 3. Then we're going to use that to find our circumference. Circumference is 2 pi r, so we have 2 times pi times our radius 3, and so our circumference is going to be 6 pi centimeters. No square on it because the circumference is a length measure. It is basically your perimeter of your circle. Now let's talk about finding the area of a regular polygon. The center of a regular polygon is equidistant from the vertices. The apothem is the distance from the center to a side. Okay, so here the apothem is CB. The central angle of a regular polygon has its vertex at the center and its sides pass through consecutive vertices. Each central angle measure of a regular n-gon is 360 divided by n. That's one of the early concepts we did in Unit 7. To find the area of a regular n-gon with the side length s and apothem a, you divide it into n congruent isosceles triangles, because if you notice, each of these pieces is an isosceles triangle. And so since we have 5 sides on this pentagon, we have 5 isosceles triangles. So the area of each triangle is 1/2 a times s. A is our height, our side length is our base for this triangle. So we just found the area of the triangle. The total area of the polygon is n times that area of that triangle. Or you can say 1/2 area times the perimeter, where the perimeter is the number of sides times the length of the side. So that gives us the area of a regular polygon. Area is 1/2 the apothem, where the apothem is that center to the side, perpendicular to it, times the perimeter. So let's do a couple of examples. Find the area of a regular hexagon with side length of 6 meters. Well, we have to do a little bit of figuring. To find the apothem, you have to use some of your triangle knowledge. Split your isosceles triangle into 2 30, 60, 90 triangles. You know the short leg is 3, so your long leg is going to be 3 square root of 3. This goes back to things that we did in our triangle units. So the apothem is 3 square root of 3. So from here, we do 1/2 of our area times our perimeter. Well, our apothem is 3 square root of 3. Our perimeter is going to be 6 times 6, which is 36. And so that's going to give us 54 square root of 3, which is approximately 93.5 meters. In example 8, we're going to find the area of a regular pentagon with side length of 8 inches. So here we have to use a little bit of trigonometry because we don't have a special triangle, but we can use trigonometry to find what our apothem is. So the central angle is 360 divided by 5, which is 72. Half of 72 gives us 36. So this angle is 36 degrees. We know that since the side length is 8, this leg of the right triangle is going to be 4. So we're going to use tangent, opposite over adjacent. So our tangent of 36 degrees is going to be equal to the opposite, which is 4, over the adjacent, which is a. And then we're going to rearrange this in terms of a. So our apothem is going to be 4 over the tangent of 36 degrees. And we're going to leave it that way. And we'll plug it into our apothem, or our area formula, like that. So we have 1/2 of the apothem times the perimeter. We know that our apothem is 4 over the tangent of 36 degrees. And we know that our perimeter is going to be 40 because each side is 8. 8 times 5 sides gives us 40. Now, if you put all of this in your calculator in one go, you can put it all in, parentheses and all. You're going to get 110.1 square inches. All right, we're going to finish off this section by talking about perimeter and area in the coordinate plane. So a method of estimating area is to use a grid and count the squares on the grid. Recall the distance formula used to calculate distance and the slope of a line containing the same points. We're going to find the area and perimeter of the rectangle that is given here in this figure, and we have the vertices all laid out for us. So what we're going to do is we're going to say, since we know this is a rectangle, we're going to say that our base is CD, and we're going to say that our height is BC. Okay? So for our base, we are going to find the length of CD. So we're going to use the distance formula to achieve that. So -2 minus 4 squared plus -3 minus 0 squared. And that's going to give us a square root of 45, which simplifies to 3 square root of 5. Our height, we said, will be BC. And this only works because we are told that this is a rectangle. Otherwise, you would have to use slope to determine if it is a rectangle using the methods that we used when we were determining if a parallelogram was a rectangle. So you've got 4 minus 2 squared plus 0 minus 4 squared. Again, we're just using the distance formula to find the length of this using the coordinates here. So here we have the square root of 20, which that reduces down to 2 square root of 5. So now, to find the perimeter, we are going to add the sides. So the perimeter is equal to 2b plus 2h. So we have 2 times 3 square root of 5 plus 2 times 2 square root of 5. And when you do all of that math, you're going to get 10 square root of 5 units. For the area, we're just simply going to do base times height. So we have our base, which is 3 square root of 5. We have our height, which is 2 square root of 5. 3 times 2 is 6. 5 square root of 5 times the square root of 5 is 5. And so that gives us 30 square units. So this is one method to find the area of a figure in the coordinate plane. If we know what the figure is, we know what shape it is, we know what formula to use, and it's just a matter of finding the side lengths that we need to achieve that. Now for a figure in a coordinate plane that does not have an area formula, it may be easier to enclose the figure in a rectangle and subtract the areas of the parts of the rectangle that are not included in the figure. So to do that, we're going to start with the area of the rectangle. And this is easy enough to determine because our rectangle that we have drawn around our figure is oriented with the coordinate plane. So our base is 1, 2, 3, 4, 5, 6, 7, 8 across. And our height is 1, 2, 3, 4, 5, 6, 7. So we're just simply counting there. So we have 56 square units for the area of the rectangle. Now we need to find the area of the triangles. So we're going to find the area of triangle A, B, C, and D. Well, we know that the area of a triangle is 1/2 of the base times the height. So for triangle A, our base here is 1, 2, 3, 4, 5, and our height is 1, 2, 3, 4. So 5 times 4 is 20. Half of that is 10 square units. And then we're going to do that for the other 3 triangles using the same area formula because they are all triangles. So it's just a matter of getting the information we need for each one and doing the math. So a little bit tedious, but nothing particularly difficult. So the base of triangle B, let's call that 3, and let's call the height 2. So 3 times 2 is 6. Half of 6 is 3 square units. For triangle C, our base is 2. Our height is 1, 2, 3, 4, 5. So base of 2, height of 5, we get 5 square units. And then for D, we have base of 1, 2, 3, 4, 5, 6, and a height of 3. So 6 times 3, which is 18. Half of 18 gives us 9 square units. So now the area of the polygon, and I'm actually going to type this part just so you can read it a little better. The area of the polygon is going to be the area of the rectangle minus the area of the 4 triangles. So the area of the rectangle is 56, and we're going to subtract the 10, the 3, the 5, and the 9. And that's going to leave us with 29 square units. So the area of our polygon is 29 square units. All right, so that finishes off section 1, talking about 2-dimensional figures. I didn't talk a lot about perimeter. We did a couple of perimeter things in here, but I trust that you can find the perimeter of a polygon because it's just a matter of adding up all the sides. Okay, if you can add up the sides, you can find perimeter. Coming up in the next section, we're going to move on to 3-dimensional figures.